Entonces, aló, bueno, para los que no me conocen, soy Alejandra Valencia, profesora del Departamento de Física, y pues it is a pleasure to, to introduce to some of you, but other ones already know Professor James Thompson from GILA, NIST in Boulder, Colorado. So today we are going to continue with our activities with the celebration of the International Year of Quantum Science and Technology. And in that context, we will have the pleasure to listen a public talk, actually, so for a general public audience, from Professor James Thompson, telling us about quantum certainty. There is no misspelling there. Quantum certainty and quantum fuzziness. So thank you, Professor Thompson, for being here. And so, okay.
Good morning, everyone. Let's see. Let me start so I know when to be quiet. Perfect. So it's been a wonderful time here. I've really enjoyed being on the campus, talking with actually many of the people I'm seeing in the audience here. Thank you for the wonderful questions and conversations during the time here. I'm going to be telling you a little more of the story and at a very high level about the idea that in quantum science, we actually have two concepts. We have a concept of quantum certainty and quantum fuzziness, or quantum uncertainty. And really, this is the one that often gets talked about in quantum mechanics, but I really want to emphasize that actually both of these are present, and they're very important for quantum technologies and for quantum science, the things we do. So, at a very high level, I'm up late, I'm working, and I look over at the clock, and, I try to tell the time and say, well, okay, maybe I'll be up till 1 this morning because I've got more stuff to do. But, if I'm particularly tired, I look over at the clock, my eyes are tired and they can't sort of correct for my astigmatism and things get blurry, right? And it's really noticeable, right? I looked over and I was like, why are there 2 clocks on the wall? Things get blurry. And, I have glasses and, I can put on those glasses, and when I do that, I can make the clock less blurry. I can fix that. But it turns out that in quantum mechanics, there's a fundamental kind of fuzziness or blurriness that you really can't fix just by doing a better job, by just doing a better experiment in the system. And so we can they get fuzzy and they stay fuzzy. It's not just that like we're building bad experiments in our system. So let's see. I have to figure out which screen I'm going to look at here. So how can we sort of work in a world where sort of this quantum fuzziness or quantum uncertainty actually is apparent, and we notice the world of quantum mechanics? And so, maybe you've seen this Marvel movie of Ant-Man, and Ant-Man sort of goes very small, and then there's the quantum world. Okay, there's nothing right about that movie. But man, it was great because, like senators' kids went and saw this movie and came home and said, hey, Dad, hey, Mom, there's this amazing quantum stuff. You should fund that, right? I was all for this movie. Nothing right about it, but I was like, this is great. So the idea is that, somehow what they did get right is often, not all the time, but often in order to get into the quantum world, we've got to get really small. That's where we can access it the most. So if we think about the things that are small, in particular, we know that we have sort of this periodic table over here of the elements, and that these atoms are actually pretty small, right? And that's exactly the kind of world where it matters. And so we like to actually take advantage of these small objects. Let me get a little closer to the changer. Changers, let's be clicked on. PowerPoint. Try again. It's changing there, but not up there. Interesting. There's a quantum uncertainty going on in PowerPoint at the moment. See if I click in some spot. Nope. Let's hang out. How was everyone's morning? What did you have for breakfast? I had some nice eggs at the hotel. How about you? It's delicious. They're very attentive. I've had arepas every morning. It's been very nice. Um, I'm in a good mood. I'm in a relaxed mood. It's all good. Exactly. It's still all good. I had a good breakfast. Should I try it one more time? Ah, there we go. So one of the reasons that you've heard this week, that you've heard a lot of yammering, that sounded mean. That's not what I meant. I just meant a lot of talking about using molecules and atoms. And you might ask why? Why is it that Anna Maria Ray, why is it that Eric Cornell, why is it that Junyi talked about using atoms? And it's because we can really get them into this quantum world and really exploit their quantum properties and leverage that to do interesting things. And so that's really what we love. So just to remind you, what's the difference between being at the very large, say at the scale of our solar system over here, compared to the very small, is that when you go very small, you realize that there's a kind of fundamental kind of fuzziness that you can already identify here, and you learn this in chemistry. Actually, often we learn about quantum mechanics first in chemistry, that somehow the electron kind of spreads out in its orbit around the nucleus over here. That's very different from the orbits of the planets around the sun, right? That they can sort of do whatever they want. They can be at any position, but they're at just definite positions, and this is the classical world. Here, they go into these discrete energy states or sort of orbitals where they actually get sort of spread out, okay? And so that's an example where suddenly quantum mechanics becomes manifest. The result of this kind of smearing out is that, for instance, if we take a gas of some atoms, in this case hydrogen atoms, and we send some electrons through them, the electrons hit the atoms and they sort of excite the atoms, right? They put energy into the atoms. And then if you look at that, by eye, you see this pretty glow over here from hydrogen being bombarded with electrons. But if you look more carefully, in fact, if you kind of send them through a prism, you notice that there are these discrete colors. It's not just a continuum of colors. It's not like you go out and you look at a rainbow in the sky and you say there's just a continuous sort of change in colors you go across the rainbow. No, there are these discrete colors, okay? And what's on the vertical is that we associate a wavelength or a length scale associated with different colors called the wavelength of the light. And so we can do that. We can say, this almost looks like a kind of fingerprint. Look, hydrogen has this fingerprint of different colors that it generates. But now we can do a different gas, and we can say, for instance, put neon in there, and it has a different color, just so in steady state, it looks a little more sort of orangish, yellowish. But we actually split those colors out again using a prism, and you see that the discrete colors are different. So each of these atoms have a definite fingerprint. And the reason for that is coming from quantum mechanics. We'll talk about where that's coming from. I think many of you know, but we'll talk about that in just a little bit. But let's talk about why that's useful. And the reason for that is that all of these atoms are identical, so that every hydrogen atom will emit the same colors, and every neon atom will emit the same colors. Let's make the analogy. Imagine I wanted to build something. Like I wanted to build, say a clock. Here's a water clock. This is an ancient water clock in China, where essentially some water wheel got turned, and basically that flow of water in some sense set the flow of time. It's how they measure time, by that flow of water. But let's say you want to build two of these, would they be identical? And the answer is no, because the flow of water matters. It was a big deal in my life. The time came when actually we were able to clone animals. And so clones are identical, right? And so again, you would say, well, they are at some genetic level. But in reality, what you begin to notice is that, this one fell down in the grass and skinned its knee, and this one had, sort of a bite on its ear or something like this. And really, they're not identical. And the reason for this is these are these big macroscopic objects that actually live in the classical world over here. And in the classical world, it's really hard to make things identical. Coming back to atoms, we have this beautiful fact that instead of having this classical picture of the atoms orbiting the nucleus and sort of some kind of Bohr model here, but really more of a classical model, the atoms actually end up in discrete orbits. They can only be in discrete sort of trajectories around the nucleus of the atom. And this leads to discrete energy levels within the atom that the atoms can occupy. Now, what's great about that is if I take a particular atom and I look at the colors of light emitted on Earth, because of these discrete levels, if someone else on another planet were to take the same atom and measure the colors, they should be exactly the same, right? Which means that independent of who's doing the experiment, they should get the same results. And that's really what quantum mechanics gives us when we work with atoms and molecules. It really gives us a kind of quantum certainty principle system. How can we leverage that? So let's play detective with the night sky, right? So you look up with a telescope and you look at some galaxy here through a telescope, and you can take the colors coming out of this sort of galaxy here. You can take a spectrum. And it turns out that when you do that, you can look at sort of light coming from one end of this galaxy and from the other end of this galaxy. Let's call that the left end and the right end of the galaxy. And there are some atoms that are the same type of atom that emit light at the two ends of the galaxy. But when we actually take a spectrum from the left end to the right end, this is just one single line over here, say, you notice that actually it shifts sideways. So this is wavelength or color. You see that on one end it's shifted to the right, and on the other end it's shifted to the left. And from this we say, but wait a minute. These are clearly the lines that should be emitted by hydrogen, but for some reason they're different in different parts of the galaxy. But we believe in the quantum certainty principle. And so therefore something else must be different. Why are they shifting? And what we can tell is that this is arising from the Doppler shift. It's the fact that one part of the galaxy is moving towards us and the other part of the galaxy is moving away from us as it rotates, right? And by doing that, we can actually figure out exactly how fast this galaxy is rotating. And we're nowhere near it. But we're leveraging this concept of quantum certainty system in order to help us. In fact, this is very powerful because people go out and they make measurements of the universe and they say, look, let's look at how fast these things are rotating. You say they seem to be rotating too fast, but there's not enough gravity from the matter that we see. And so in fact, we believe that by looking at all these rotations using this quantum certainty principle, that we can actually look out in the universe and say there must be some type of matter, which for lack of creativeness, we have called dark matter. We just mean that it doesn't emit any light that we can see in our telescope, but we can see that it must be there because otherwise these galaxies are spinning way too fast and they'd fly apart. You might think, okay, well that's funny, but maybe a curiosity. In fact, it appears that the vast majority of the universe is actually composed of dark matter. It's not the stuff you and I are made out of in order to explain all this. It tells you that we think of physics as being sort of kind of solved, like we've done a pretty good job at figuring out physics. But in reality, we haven't figured out most of the universe at this point. Cool. Again, I want to sort of emphasize that we can do this because of this quantum certainty that's offered in these systems. In fact, we believe so much in this, and this has been so consistent, that rather than having these sort of classical clocks based on various other sundials, orbit of the Earth, we can build things called atomic clocks. Those atomic clocks allow us to make these comparisons between laboratories and between clocks in different locations in the same town, and we can actually define time in terms of, say, the ticking rates of atoms over here. So it turns out you've heard some of the best atomic clocks are actually located in Boulder, and they can sort of measure sort of their timing precisions out to the 18th to 19th decimal places for differential measurements between two clocks. They can get out to 21 decimal places. Okay, you can see I recycled this slide. There was a museum in Miami, and I was giving this particular slide, and instead of the Frost Museum, you should think about how to get to this auditorium. Don't go to Miami right now. Stay right here. But the idea is, how do you know to get there? We've all become spoiled. On our phones, we have Google Maps or Waze or whatever you have that tell us, hey, look, turn right now. And the way that works is actually that you have a constellation of satellites up in space. And that constellation of satellites is ticking, and essentially they transmit tick, tick, tick. They're broadcasting that. And receivers on the Earth are looking at the relative arrival of the ticking rate of the ticks from different satellites. And from doing that relative timing, they can figure out where you are on the Earth. So I really wanted to emphasize the power of quantum mechanics in terms of leveraging it to make very precise measurements of our universe. Even parts of the universe we can't actually touch, things far away from us. But I really have to come back and say, yeah, but there is this other part of quantum mechanics, and that's the part that gives us an uncertainty or fuzziness in the system. So I kind of like to think of it as, quantum mechanics gives and quantum mechanics takes, okay? So now we're going to talk about the part of quantum mechanics that can make your life hard, okay? It's this quantum fuzziness. So you'll see throughout this, I'm not going to really explain in any serious detail what I'm really drawing here, other than to say the kinds of systems I'm going to talk about, we think of them as often some kind of sensor that has some kind of like meter. It could tell you acceleration or magnetic field, or in this case, I drew it like a clock to look like time, an atomic clock. But in fact, instead of being a two-dimensional object, we describe these as three-dimensional objects, and we have a fancy word for it that you might hear slip out of my mouth called the Bloch sphere. And in reality, we sort of care about sort of reading out one dimension, sort of one orientation of this clock hand called the Bloch vector. Okay? And there's some fundamental quantum fuzziness that sort of precludes our ability to measure the orientation of our hand or meter hand or our clock hand with infinite precision. So I said that sometimes things get fuzzy, and we put on our pair of glasses and things don't get better over here. And so we're kind of stuck. But what I'd like to tell you about a little bit is that where does that fuzziness come from? Let's actually start with that. Okay. So my kids went to an elementary school. We live near the mountains, so we have bears that sometimes wander into town. They go through the trash cans, things like this. So one of the local elementary schools is called Bear Creek Elementary, and that's where two of my kids went. And if they go to Bear Creek Elementary, they're learning how to do math. And you would say, well, look, is 2 times 3 minus 3 times 2 equal to 0? And they write that down. And they say, yes, that's equal to 0. A+, right? They do really well. But on the other hand, if I had sent my kid to Quantum Elementary School, we would have looked at it, and if they had given this answer, they would have gotten an F. Now, I don't know what the grade scale here is in Bogota, but F means fail. Got it wrong. And in fact, in quantum mechanics, this quantity is not equal to 0. Now, this is sort of a high-level sort of version of what we call commutation relationships, that the order in which you do something matters, okay? So it's sort of another way we like to phrase this to give something that's a little more connected to what you might think about is that in quantum mechanics, you might ask where is something, and then ask how fast is it moving, okay? Or you could ask the question, how fast is it moving, and then ask where is it? And when you ask those questions in different orders, you don't get the same answers. So it really is that this sort of ordering of how you ask these questions leads to something called the Heisenberg uncertainty principle, which is essentially this quantum fuzziness up here. And so this idea of there's some uncertainty, delta in atomic physics, in physics, we often think of it as like uncertainty in something. The uncertainty in position, which is x, times the uncertainty in momentum, which is sort of how fast you're moving, has to be greater than or equal to 1/2 h bar. H bar is something called Planck's constant, which is sort of a constant of the universe that sets the scale, sort of a scale at which quantum mechanics becomes sort of visible, that you begin to notice it. Okay. So for instance, here's an example. Here's Lightning McQueen, and you could ask, how fast is Lightning McQueen going here? And you could say, well, classically, he would have some position and he'd be going so fast all around the racetrack, and you could put a little vector representing where and how fast at the same time. But in quantum mechanics, the product of this uncertainty, says that actually there's some fundamental quantum fuzziness that you really can't specify where he is and how fast he's going to better than this sort of circle here. That there will be fluctuations when you go and repeat the experiment many times. Now, why don't we notice this quantum uncertainty in everyday life? Why aren't we having traffic accidents due to it? Things like this. It's because it's very small, and it has to do with the fact that h bar is really, really small. H bar actually has a units of angular momentum, which is basically a kind of physics way of measuring sort of how rotatey are you, like how much rotation do you have. And so when I think about rotation, I also often think about sort of figure skaters, and they're sitting here and they're spinning around in a way that would make me dizzy and sick. But imagine you took this figure skater and you gave her h bar of angular momentum. This is about how many years it would take for her to go around once. That's how small h bar is. And it's in part because she's so big. Well, they're very petite. But relative to what we normally think about with atoms, she's quite large. On the other hand, if we could shrink this sort of figure skater down to the size of a hydrogen atom, then in fact, per second, and I'm not even going to bother, but that's probably about 10 to the 15 revolutions per second. About 10 to the 15. That is a 1 with 15 zeros after it. That's a lot of revolutions. So size really matters for seeing this uncertainty. Now, when this was first developed, there was a lot of philosophy that went along with it. People were really worried because in Newton's day, you have sort of pool balls and they're sort of deterministic. And in fact, people worried about moral philosophy of like, how can someone be responsible for having stolen something from a store if really their sort of behavior in life was determined by classical physics. It was already predetermined that they were going to do something bad. How can they be responsible? And when quantum mechanics came along, they said, well, maybe this introduces some uncertainty that allows people to be responsible for their own actions. Okay? You may not know this story, but during the Olympics, there were these two figure skaters, and she hired someone to hit this one in the leg with a big metal bar. It was a terrible, terrible thing. So we could worry about that. We could worry about, are we responsible for our own actions and things like that, but I kind of feel like maybe that's not the interesting question anymore. The more interesting question to me is, when I think about how atoms and like nuclei and electrons and atoms interact, this thing is positively charged, the nucleus, over here, and the electron is negatively charged. And I know that sort of opposite charges attract. So this electron should basically just go zooming into the nucleus and stick inside. And that's the end of the world as we know it. Because if that were true, we wouldn't have chemistry. And so I find that to be a much bigger problem than sort of moral philosophy. And so, in fact, I want to point out that really this quantum uncertainty, that's what's encoded in a thing we call the Schrödinger equation. It says that in some sense, as you make localize the electron closer to the nucleus, that you increase the uncertainty of momentum or speed, which increases the kinetic energy of the particle. And so you get a balancing act where, sure enough, the electron wants to sort of shed energy and go to a lower energy state by getting closer to the nucleus. But as a result of doing that, it becomes more localized in space. And then actually the uncertainty of momentum has to go up as a result. And in fact, this is what stabilizes all of chemistry. That's what's in the Schrödinger equation. That's what gives us these very nice orbitals and discrete energy levels. Great. We have this fuzzy clock, and now what I'd like to tell you about is efforts in my lab to build sort of not just a normal pair of glasses, but actually a pair of quantum glasses. Okay, something that can actually do something about this clock. Now what you'll see is, see how fuzzy it is, and now I'm going to put on my quantum glasses and see how it becomes a little more clear. It doesn't become crystal clear, but it becomes more clear. And so you can still do a better job at measuring time. Okay. The way we're going to build these quantum glasses, we're going to use a concept called entanglement. I'm not going into the details of it, but you may have heard of it. Sometimes, Einstein actually hated this. He referred to it as spooky action at a distance. Einstein was amazing. He was right about a lot of stuff. He was wrong about this one. In fact, this stuff is real, and we can use it, manipulate it, and it exists in our universe. And it becomes a tool that we can use. So how do we do these experiments? Here's sort of a panorama of my lab. You're going to see very simple pictures and cartoons that get to the heart of the physics. But I want you to get a sense of that these are relatively complex experiments spanning multiple optical tables, lots of electronics, lots of lasers, lots of vacuum chambers to hold these atoms and keep them in the quantum world. As a starting point, you heard from Anna Maria in her talk about the idea of laser cooling, where you basically take lasers and you shine lasers on the atoms from 6 different directions. So no matter which direction this big bowling ball, which is the atoms, is moving, there are little photons that are sort of bouncing off the bowling ball in such a way that actually no matter how it moves, it sort of gets a resisting force that actually brings it down to slower and slower velocity. And if something's moving very slowly, we call that a low temperature. So this is a picture, taken with an iPhone in my lab of a cloud of rubidium atoms. It's an atom in the first column of the periodic table. And we're shining laser light on them. And that laser light is being scattered, and we can actually just take a picture of it. So this is about 10 to the 6 to 10 to the 7 rubidium atoms at a temperature that's about a millionth of a degree above absolute zero. So these are very, very cold objects, much colder than, for instance, you can get in dilution refrigerators or even by turning down the AC in your hotel. Great. Having gotten them cold, we also would like to hold on to them and trap them so we can manipulate them. And so it turns out that we can build tractor beams for atoms. UFOs don't just have them, we have them too. We can suspend these objects. And so here's an example of an experiment in my lab where if you look carefully, this is why I wanted the lights down low. This is atoms being slowed, they come down, and they're being loaded into a tractor beam here, and now they glow blue. Those are strontium atoms. They're glowing a nice 461 nanometer blue. Okay? So we can actually suspend them, hold them for, in my lab, we tend to go for of order a second. Sort of about the best you can do these days is an hour with neutral atoms to 2 hours, something like that. So this is collecting, again, maybe about 10 to the 6 to 10 to the 7 strontium atoms. Turns out that you can actually very tightly focus these laser beams down, and you can actually do it such that you can actually trap single atoms and image them. This is from my colleague Adam Kaufman's group at Gilla. And what you're seeing here is an array of single atoms. So this is the sort of laser light being scattered, taking a picture on a camera of single atoms. And you can actually move them around, rearrange them in time, let them interact, and people are building quantum computers out of this at this point. We've got actually 2 companies in the Boulder area that are doing that with neutral atoms. You can also do quantum computing with ions. We have another quantum computing company called Quantinuum that also is doing this in the Boulder area. Okay, so we've got some control of these atoms. Eric said this, and this is absolutely true, that it's not that we invented these in our lab. There's actually a long lineage of quantum control freaks over here. And in fact, many, many, many people contributed to sort of all these tools that we have. The ones that are highlighted have some association with either, these are all in Boulder, these 4. This individual, these 4 are all at NIST. He just happens, this is Bill Phillips, who was very inspirational for Anna Maria Ray as a graduate student, and he's at NIST, but in Gaithersburg, Maryland. Great. So I've told you that all these individual atoms, we can trap a lot of atoms, we can sort of hold on to them with our tractor beams, we can control their quantum states, we can manipulate them, but what else can we do? I think one of the things that I talked about, looks like this is a repeat slide, so let's go through it, is defining time itself. But in reality, a lot of these experiments, like defining time, they use many atoms to beat down the quantum fuzziness or noise of single atoms. But can we actually somehow build new states or entangled states where the atoms sort of work together to be quieter, to reduce the quantum fuzziness? So now these atoms are connected by this sort of ephemeral thing called entanglement. The way we do that is we put the atoms between very highly reflecting mirrors, and we let light bounce back and forth about 100,000 times. And by doing that, it allows them to interact with each other via that light field and build entanglement in the system. And in particular, some of the experiments I'm going to tell you about is this vertical cavity where we have laser-cooled atoms that are trapped and they're allowed to move along the cavity axis here, interacting with the light. In particular, okay, is Futurama a thing here? Yeah, I love Futurama. You know, one of the things we use is actually the quantum measurement process. So, you know, here's this horse race. It's a dead heat, you know, and then they're checking the electron microscope to see which horse won. And the winner is number 3 in a quantum finish. And Farnsworth is the bad guy. No, Farnsworth, right? Good. It's been a while since I've had a chance to watch. He says, no fair, you change the outcome by measuring it, right? And this is exactly what happens in quantum mechanics. That in some sense, the quantum measurement process actually fundamentally changes the state of the system. That's one of the weirdest parts of quantum mechanics in my view. That's really at the heart of what quantum mechanics is. So I'm not going to go into detail, but the basic idea is we start with some atoms that are not entangled, and they have some quantum fuzziness that obscures our ability to make a quantum sensor or a quantum measurement over here. And what we essentially do is we measure the orientation. We make a very special measurement using our cavity system that allows us to just measure the orientation and prepare a state that has reduced uncertainty. We prepare a sharper clock hand over here for whatever measurement we want to make. So we use that measurement process itself to create the entanglement. That's about the level I'm going to explain it at today. I talked about it a lot at the technical talk yesterday, but come up and ask me questions if you were not there and you're interested. I will also say, again, I'm not going to explain it too much, but there's another way we can create an entanglement where we essentially build a kind of interaction where the atoms can sort of emit photons into the cavity and reabsorb them, and different atoms can exchange and emit photons in such a way that you can conceptualize this sort of block sphere over here as a big rubber ball. So imagine that it's a big rubber ball, and now I'm going to sit down here so I can use my hands, and then I'm going to be very loud. Imagine you had a big rubber ball, and you drew a little circle on it, which represents the quantum uncertainty. Now you grab the North Pole and you grab the South Pole, and you twist in opposite directions. Then you know what happens to that rubber ball is that, well, at the equator, halfway in between your hands, nothing moves, right? But if you're closer to the North Pole, you'll follow the hand at the North Pole. If you're closer to the South Pole, you'll follow the hand near the South Pole. So what that leads to is that you get a kind of shearing of the quantum noise. So the quantum noise that's further from the equator moves to the right. The quantum noise that's further from the equator, below the equator, moves to the left. And if you apply this for some amount of time over here, then you see that actually you shear into a reduced uncertainty state along this direction. And having produced that state, we're really good at rotating these things around. So now we've prepared this state, we can use it as a resource. So this is another way in our lab using what we would call Hamiltonian dynamics or unitary dynamics that does not involve the measurement process in order to create this entanglement. Okay. This process, for people who'd like to know, is called one-axis twisting. That's what we're doing. Okay. So again, I'm not going to explain how to do it. I basically put this up to say, there's a Rube Goldberg machine. Do you know what Rube Goldberg machines? Is there a version of that in Spanish? It just means like a complicated, very complicated, like the ball rolls down that hits the matchbox, which lights the match, which then burns the string, that then drops. Like it's like that, okay? And that's what all this is about, okay? That goes into doing that. That's the Rube Goldberg machine. Now, in reality, in Rube Goldberg machines, the idea is that you make it excessively complicated more than you need to actually accomplish what you wanted to accomplish. But in this case, in fact, we do need all of this to accomplish what we do. Great. So here's some example of this quantum noise. I said there's quantum noise. And if you look over here, you'll see that here are two quantum states that I could prepare with their quantum fuzziness. And if I measure, in this case, we're actually measuring this way. Don't worry about it. Pretend like I measured this way. It's not so important. the projection or the orientation along this axis, this horizontal axis. Then I repeat that experiment. I do it many times. From one trial to the next, I get scatter. Okay? And what you're seeing, that scatter, is almost pure quantum noise. It is the quantum fuzziness that obscures our ability to tell the orientation of these two hands. On the other hand, if we create these entangled states, they're sharper pointers, and now we can actually distinguish these two states much better, and we can tell time, acceleration, rotation, magnetic field, whatever we're measuring more precisely in these systems. This reduction in the quantum noise is a direct quantifier of entanglement in the system in terms of something called the quantum Fisher information. So we've been working in our lab, and I'm just going to highlight it, to apply this to a type of quantum sensor called a matter wave interferometer. This is something we build in atomic physics. It's very powerful. It allows you to very precisely and with high accuracy measure accelerations and rotations. And the basic idea is this. If I have some atoms coming along, I can apply a pulse of light, and the atom can absorb a photon or not absorb a photon. But if it absorbs a photon, photons carry momentum. And from conservation of momentum, the atom must recoil if it absorbed a photon. And so what happens is the atom would recoil, change its trajectory in space. But if it didn't absorb the photon, then it would just keep going. So what if we tune our lasers just right so that we put the atom in both a state where it absorbed the photon and didn't absorb the photon? And when we do that, it means that the atom both recoils and doesn't recoil at the same time. That concept is called superposition. And in this superposition, we can let the atoms move apart in space, apply another pulse of light that in some sense flips the parts of the, what we call the wave function, of having absorbed or not absorbed, and actually reverse this process, bring the sort of these two parts of this atom being in two places at once together and interfere them. It turns out that if you have an acceleration or rotation during the middle of this, what we call an interferometer, but with matter waves, the wave nature of the particles, then in fact you can measure these accelerations and rotations very precisely. So there are all kinds of technology applications. People would like this for GPS-free navigation and gyroscopes. They're very important. They probably already exist in various applications. We're probably just not allowed to talk about them. I don't know what they are, but I think they're out there. For accelerometers, for measuring gravity and for gravity gradients. It turns out, and this is related to some work I did in my PhD as well, that it also allows you to make determinations of the fine structure constant, the 1/137. And it does in a way that's very, very insensitive to theory. You don't need a lot of theory input. And as a result of that, it allows you to take that fine structure constant and compare it to use QED to predict what the G factor of the electron is. The fact that the electron has a little magnetic moment, and there's this thing called the G factor in quantum mechanics that is very important and is sensitive to new physics. And it turns out that you can now sort of combine these and measure and test QED, quantum electrodynamics, out to 12 decimal places. There are lots of other tests, including searching for dark matter, dark energy, for exploring the world around us, as well as sort of measurements associated with gravity over here. So these are amazing things. And one of the questions we had is, can we actually use this idea of squeezing, where we squeeze the quantum noise out of one direction and put it in another direction? Can we use it in a matter wave interferometer? Now, before doing that, I want to emphasize that I told you about these matter wave interferometers and the idea that you're in two places at once. But I want to emphasize that this is a very macroscopic thing, or can be. At Stanford University, Mark Kasovich's group has a 10-meter tower in which he does matter wave interferometry. And at the top, he launches the atoms up, the two wave packets separate at the here and here, and then they take a picture of the cloud. This is the picture, okay? They shine laser light on the atoms up here and ask, where are the atoms? Here's one peak, here's the other peak, and they're separated by half a meter. The atoms are really being put in a superposition where they're at sort of half a meter apart at the same time, and coherence is maintained. So this is really sort of what we're trying to say, well, look, okay, great. Let's now see if we can introduce entanglement into these types of systems and make them even more sensitive. Mark Kasovich with Jason Hogan and others at Stanford, Northwestern, and other places in the US are building these kinds of experiments as searches for dark matter and also for gravitational wave detection. And we'd like to bring entanglement to those systems. So here's the upshot, that we can actually realize this, what we call measurement-induced squeezing, or this one-axis twisting, to generate sort of entanglement inside this matter wave interferometer, where the north pole is one arm of the matter wave interferometer, and the south pole is the other arm of the matter wave interferometer, and then we map it back onto this block sphere. We can actually map it back onto what we think of as, we call it a two-level system. One level is one arm, the other level is the other arm. There's a quantum uncertainty. We create this squeeze state. We then actually initiate the measurement for the matter wave interferometer here. We wait some amount of time, we re-interfere, and then we reproject back onto the vertical, and we can see that we have a sensitivity below the quantum fuzziness level that we call the standard quantum limit in our system. So I've told you about reducing quantum fuzziness and using entanglement. We've also applied this in atomic clocks in collaboration with Uniandes group. We're taking the techniques that we've developed and pioneered and taking them down there and applied them to strontium optical lattice clocks. But I don't want to talk about that. I'd like to now switch gears and talk about another type of fuzziness that we combat in our lab. Okay. This one doesn't fundamentally come from quantum mechanics. It actually comes from the classical world, but it turns out it's really, really important. And in particular, when we build very stable frequency lasers, it turns out these are very, very useful for building atomic clocks and for building very precise measurements of the world around us. It turns out there's a fundamental kind of fuzziness that's actually related to the finite temperature. It's actually a thermal fuzziness in the system. What we're going to do is we're going to try and get around this using our atoms by keeping all the sensitive information that we care about primarily in the atoms and not in the light field of this laser. So here's the context. If you want to build a very, very good stable frequency laser, you take two mirrors and you put them on some hunk of material with a separation that may be of order 0.5 meter to 1 meter. And those mirrors are very reflective, and just like the length of a guitar string, sets the note that you hear, there's a resonance associated with this spacing of the mirrors that's an optical or a light resonance. And you stabilize the frequency of a laser to match the resonance frequency of these two mirrors. They're separated by the separation distance. That resonance frequency is set by that. So we all have buddies, right? And sometimes buddies come to you and they say, hey, look, hey, could you build me a laser that whose frequency only drifts by a part in 10 to the 17? Yeah, we all have friends like that, right? Well, it turns out in Boulder we have a lot of friends like that. And you say, okay, yeah, sure, no problem. I'll get on it. I'll get back to you this afternoon with it. You could take it away. But now you start putting in numbers. You say, I'm going to make the mirror separation 1 meter. And now you ask, in order to stabilize the resonance frequency to 17 decimal places fractionally, I need to control the mirror separation to 10 to the minus 17 meters. And you might remember that the size of a single nucleus is about 10 to the minus 14 meters. And now you think, well, okay, don't come back this afternoon, come back tomorrow, okay? And so you sort of say, okay, I'm going to get rid of all the noise. I'm going to get rid of vibration noise, the people stomping around, people opening a soda can, buses driving by, all this stuff. You get rid of it with vibration isolation stages. And yet it still looks like things are vibrating. And it turns out that the reason is something that was explained by Einstein, which is thermal Brownian motion. All the atoms that compose these objects are made of real atoms, but these are atoms at finite temperature. They're jiggling. That causes the separation to change. People have spent many decades on this now, trying to make this better. And in fact, this is a big deal for LIGO as well, the interferometer that tries to detect gravitational waves. So, hard problem. People are making amazing progress, including Juni's group, who has basically the best laser in the world using these techniques. But there was this idea that, well, in nature, there are these transitions where An atom is in some excited state, in some ground state, and sort of, it's a very long-lived excited state. So if something lives for a very long time, because of time frequency uncertainty relationships, that also means it's very narrow in frequency. So there are atoms that have line widths of 1 millihertz, not megahertz, millihertz to hertz. Could we actually just get those delays? Can we actually get them to give us light directly and use those atoms directly as a laser? Okay. You may be used to, well, some of you may be used to normal lasers, but in a laser, it's light amplification by stimulated emission of radiation. And in most lasers we build, one way to think about it is you have some atoms or some gain medium, it could be semiconductor, but sort of there's some frequency range over which sort of that gain or ability to amplify the light exists. And here that's this sort of pink range here. It's very broad in frequency. But on the other hand, the time or the lifetime at which, sort of photons inside of this pair of mirrors that form the laser cavity, the time they live for is set by kappa, and actually that's much narrower, okay? And so in a normal laser that you would build, the photons, the light field, or the flywheel, the thing that keeps track of the memory of the phase of the laser, or sort of, should the electric field of the light coming out of the laser be up or down or somewhere in between? That's what we mean by phase. And so in this system, because this is true, the oscillation frequency follows the resonance frequency of the cavity. So if the mirrors move due to thermal motion or vibration, the lasing frequency will just follow one-to-one. On the other hand, we want to work in a regime with these very narrow, very coherent atoms so that our gain medium is super narrow in frequency on the horizontal, but the cavity is actually very leaky, and actually photons leak out very quickly. And here the atoms are going to be the flywheel or the thing that keeps track of like what the phase or frequency of the light should be, and the oscillation frequency primarily follows the atomic transition frequency. And that is sort of well-defined due to quantum certainty. So in particular, we do this in strontium, and we use this millihertz line with transition in strontium. It means it actually has a lifetime of around 120 seconds that the atom will live in this excited state. We pack many, many of these atoms between two mirrors over here. We're going to use those atoms as the sort of the amplifier or the gain inside this laser. So if you do that, how much might we win? And I won't go through details, but you can predict pretty quickly that it should be more than 10,000 times less sensitive to frequency vibration noise of the cavity. There's also some fundamental quantum noise called the shallow Towns limit. Not so important, but it turns out you can calculate how much would quantum mechanics limit the line width, and that would limit the laser line width to less than a millihertz. Great, that's much better than state of the art. Let's do that. So we built such a laser where we actually put all the atoms in the excited state, and then we waited some amount of time, and we looked at the output power from the laser as a function of time. So output power in weird units here. If we use 200,000 atoms inside the cavity, we laser cool and trap, then we get this pulse of light that comes out, and it comes out very fast compared to spontaneous emission. It's a strong stimulated process, even if it's lasting only 50 milliseconds over here. So all the atoms are going from the excited state and being stimulated to the ground state, and then it stops. In this picture here, there's a phenomena by a scientist called Dickey, who was at Princeton, who predicted such phenomena, and this is exactly what you predict for such a system, and that's why we call it a superradiant laser. Now we can ask, we get one pulse of light, then we throw the atoms away, and we create a new batch of atoms, and we get another pulse of light, and we repeat this. And we can ask, well, what is the frequency of the light that's coming out in these pulses? How stable is that? And so the first thing we can ask is, what if we shift the cavity resonance frequency? How much does the lasing frequency change by? And it looks like we're about 5,000 times less sensitive to vibration. Okay, in precision measurement, very rarely do you get to say, we have a technique that makes us like 500,000 times less sensitive to a thing that people have been like spilling blood on optical tables for 2 decades. Okay, that's exciting, okay? So we were like, hooray, this is awesome. In fact, it may mean that you can be sort of much more sloppy in your vibration isolation and maybe even make these deployable outside the science lab for applications. The other thing you can ask is how frequency stable is one pulse of light? It's about 7 times 10 to the minus 16. for a single pulse of light, and you can look at sort of how the fractional frequency and stability changes as a function of how many pulses we collect. I will point out that this already makes this the most precise active atomic clock that's ever been realized. And this was just sort of our first attempt. We can also ask about the accuracy. How close is the frequency of the light to the known strontium transition frequency by comparing to atomic clocks in June Yee's lab? And we can say we were not working hard, but it's good to about 4 parts in 10 to 15, which is also very good for such an active clock. It's so good that we're building up right now in our lab this system. I showed a picture of it earlier. It's a ring cavity with 3 mirrors. So light bounces around in a triangle. We're going to try and continuously load atoms inside of here as the gain medium in order to build a continuous source of laser light that's very narrow and very stable. And when we do that, actually, we think we can get very, very high precision. We think that by collecting light from the laser for only 1 second, you can get sort of frequency uncertainties that are a few parts in 10 to the 18. So for me, what I always remember, that you see it right there, that if a change in height about the width of your thumb, right, is about 1 centimeter, and the flow of time is different by part in 10 to the 18, okay, across there. So, you know, like the hairs on my arm are growing at a different rate than the hairs on my leg, right? And you're like, it's so slow you don't notice it, right? But it's there, and we can really measure it, and we can actually use it to explore the world around us. So for instance, there are thoughts about how to harness this kind of precision for doing geodesy, exploring gravitational potentials of the Earth, understanding what's going on underneath the Earth, for detecting gravitational waves, and for detecting dark matter in the future. Okay. One of the applications is not just sort of science applications, but also, for instance, detecting buried deposits. Okay, so for instance, maybe there's some oil, gas, gold deposits, iron deposits, whatever they are, that you can actually sort of look for these kinds of things under the Earth. The geophysical monitoring, I mentioned previously, you can use it for monitoring water tables. So for instance, if farming is happening and people are sucking water out of the ground, that you'd be able to sort of look for that. People are also interested in using atomic clocks like I'm describing, as well as the matter wave interferometers for monitoring, for instance, volcanoes and predicting earthquakes. As I mentioned, there are proposals for which I've written at least one paper of putting these kinds of systems in space at very large separations. This is actually a version called LISA. That is a version of LIGO that could go into space. The advantage of using atoms is instead of having 3 satellites, you could have 2 pairs of satellites. It should just be one pair, so 2 satellites. And it would allow you to detect gravitational waves in a much lower frequency band, where there's abundance of sources for gravitational waves. And lastly, all this quantum certainty, you know, you've heard about it. I want to come back to Eric's talk where he was talking about the EDM, the electric dipole moment of the electron, that it's exactly this kind of quantum certainty that he was exploiting to be able to ask how round is the electron, right? Like sort of, is there any kind of like charge that builds up on the North Pole versus the South Pole of the electron? And in fact, those are so precise that when I wrote this slide, they could say the electron was round. If you blew it up to the size of the Earth, it might have a bump that's smaller than the size of a virus, and now it's a few layers of atoms. They're doing this in molecules, but they're really taking advantage of exactly that same quantum certainty, and all these kind of games about making very precise measurements of the world around us to do interesting physics. So with that, I really want to highlight that science is done by people, and those people are amazing, and they collaborate, and they talk to each other, and they have a lot of fun in the lab. And so here's my group, some current and past members as well over here, as well as really fun collaborators at GILA and around the world who all make this happen. So with that, I'm going to stop and take any questions you may have. Thank you.
Are there any questions or comments in the public?
Hey James, so thanks for the talk. I have a question regarding, what do you think will be the next block that will stop you from getting getting even better atomic clocks, like the next big block?
So in the context of atomic clocks, why can't they be good to 30 decimal places? Like, why can't we go there? There are a couple of answers to that. One is you have to worry about what we call systematic errors. I said all these atoms are identical. They are if they're in the same environment. And so in reality, they're, for instance, here's an example of a challenge. They're not sitting in an environment that's at 0 Kelvin. You may have heard that in quantum mechanics, it led to the development of quantum mechanics, that even at finite temperature, there's just a glow of photons being emitted by all surfaces. We call that Planck radiation, black body radiation. And it turns out that those photons, just from the fact that the room is at 300 Kelvin, can give you very small shifts on the atomic transition frequency. And so right now, that's one of the leading shifts in, say, the strontium optical lattice clocks. And it becomes a question of how well can you define the environment, measure it, or potentially go cold and operate these sort of clocks inside of an environment that's at 70 Kelvin or 4 Kelvin. Colder is probably harder, but those temperatures are viable. And this effect, if you remember, there's a thing called the Stefan Boltzmann law. It's not so important if you don't know what that is, but there's just a very rapid scaling of how many photons you have because it goes like the temperature to the 4th power. So by bringing that temperature down, you could do much better. That's an example of systematic errors. However, I also want to say that in some sense as an experimentalist, if you have a systematic error and you have enough precision, then you can turn up the bad thing, turn down the bad thing, and see how much your answer changes by. But if it takes 2 days to ask, when I make it bad, how bad is it? And when I make it good, how good is it? It limits how many knobs you can turn on your experiment to see what's changing the answer. And so precision is intimately linked to accuracy. If you give me more precision, I can explore the systematic errors more fully, and I can actually constrain them, and I can make a better clock. I think the idea of getting out to 10 to the minus 21 is totally doable. That should be doable. That will happen. Beyond that, there's going to be a lot of dicey stuff, including the fact that, well, at what point in space are you telling me the ticking rate due to gravity? So now we begin turning around and saying, okay, we've gotten to the point where atomic clocks, having to sort of define what gravitational potential you're at, actually we don't know the gravitational potential very well. And so now we turn it into a measurement of the gravitational potential. So once you start getting out sort of into the 10 to the minus 20, we're beginning to turn these into more of like gravitational potential sensors at that point.
Well, first of all, thank you for the talk. I loved it. And I just had a quick question. You mentioned the one-axis squeezing, and well, I don't know, but I'm just curious if there's something like also 2-axis or 3-axis or more axis squeezing?
Absolutely. And it turns out that this process where you treat the sort of block sphere as a rubber ball and you twist it was proposed in a seminal paper by Kitagawa and Ueda, a pair of researchers from Japan, in around 1993 or so, 1995, somewhere in there. And in the same paper, they talked about something called 2-axis twisting. And basically, 2-axis twisting for that, I'd have to get a buddy from the audience. But let me put the microphone down for a second. You have a rubber ball. 1-axis twisting is grab the North Pole and South Pole and twist in opposite directions. 2-axis twisting is you get a buddy and you say, I'm going to grab at 45 degrees and twist. You grab at 45 degrees the other way and twist at the same time. And that's called 2-axis counter twisting. And it turns out that it's fundamentally more powerful. that you can get more entanglement from it. So the thing is, it has been a magical unicorn for 30 years. We know that it's great. We know that it would be wonderful to have. We don't know how to make it. However, about a year and a half to 2 years ago in my lab, we figured out how to make it for the first time. So for the first time, we have available to us two-axis counter twisting, and we need to improve some laser technology in our lab. We need to beat down some noise in order to apply it and generate squeezing or entanglement in our system. That's two-axis twisting. With respect to three-axis twisting, I will say we have a mechanism in our lab right now that is a first time that we realize that all of these one-axis and two-axis twisting you can model as an all-to-all two-body interaction. So it's like this atom interacts with that atom, but at the same time, that atom is interacting with that atom. But in some sense, they act at any given moment in a pairwise way. But they're doing it to every, so it's all-to-all. But nevertheless, the fundamental interaction is you push on me, I push on you. You know, it's like that. We have figured out how to build 3-body and 4-body interactions, and that gives access to sort of something that you might want to think of as a kind of 3-axis twisting, where we build, instead of what we would call Gaussian states, we can build very highly non-Gaussian states. In particular, if you started with the block vector at the North Pole, and we applied this interaction, you develop, for a 3-body interaction, we end up developing a claw. We sort of distort the quantum noise into sort of this like 3-legged object that looks like some talon on the top of the block sphere. And it turns out we're writing a theory paper with Anne-Maria right now, and it looks like that has a lot of this stuff called quantum Fisher information that actually you can use to make better measurements in the system.
Okay, thank you.
Thank you for the question.
There was around here, no? So any other comment, question?
Thank you, James, for the talk. You mentioned when you were talking about spin squeezing that it's related to entanglement.
Yeah.
So I was wondering if you measure like entanglement, you have like a maximum tangle state. Does that mean that you have also like a maximum squeezing that you can perform on your atoms?
Yeah. So darn this handheld microphone. I like to do physics with my arms and my hands. So it turns out that theorists love something called a GHZ or noon state. And what that state is, and that gives you the best sensitivity you can possibly have. It actually has a lot of limitations, and the reason in large atom systems you probably don't want to use those states. But nevertheless, I'll tell you what it is. It's basically you put the atoms in a superposition of all the atoms being in the upper state and all the atoms. And when you do this, it turns out that you saturate the best you can do, and we call that the Heisenberg limit. We have a name for it. And it just says that this is the best you can do. It turns out there's some reasons that that's not a great idea. However, for the states we've developed, if you wanted to compare to GHZ states, these sort of maximally entangled states, what I would make the comparison is, in order to accomplish what we accomplish, you would have to reach into our collection of about 1 million atoms that we're using. You would have to pull out 60 atoms at a time, put them in a perfect GHZ state. No one's ever done that. But you'd have to put them in a perfect GHZ state. You'd have to pull out the next 60 atoms, put them in a perfect GHZ state, the next 60 atoms. You'd have to repeat that 7,000 times, run your sensor, and read it out. We get the same sort of enhancement in sensitivity, not by using GHZ states, but instead using a 40 microsecond laser pulse. It's a much simpler operation to use. And I just think it's sort of very well technologically matched to the capabilities of what we know how to do in the laboratories. As an analogy, GHZ states are in principle what you might imagine sending into LIGO, but they don't. They send in squeeze vacuum, and there's a reason why. It's hard to build a laser that generates GHZ states that runs at 10 kilowatts. That's kind of the rate of, they're sending in around 10 to the 23 photons per second into LIGO, okay, the laser interferometer gravitational observatory. it's really hard to send in GHZ states at an optical power of 10 to the 24 photons per second.
Okay, thank you.
But just a follow-up. So GHC states will be the optimal ones. It's just that technically you cannot, or it's difficult to achieve, or it's not the reason really.
So there are a lot of reasons I'm not chasing in any way GHZ states. I think they're amazing, and I think they're great if your system size is like 10 to 20 atoms. And so when you're constrained in the number of atoms you can have, so for instance, in ion traps, where they build atomic clocks or they're building quantum computers in ion traps, it makes a lot of sense to build GHZ states and use those states. The problem is it doesn't scale very well. And one of the issues is that you would really like to fundamentally change the scaling of your quantum sensor, because the technology requirements in the sensitivity to single particle decoherence is much higher in these GHZ states than in these fully symmetrized squeeze states. So for the same enhancement, you're much more robust against decoherence in these things. So I'm a little bit like, as a quantum information object, GHZ states are amazing, and for when you have an experimental constraint that sort of limits you in atom number, that's a good thing to do. But if you're thinking one day, I don't want to work at 10 atoms, I want to work at 10 to the 7, and then and a decade later I want 10 to the 8. Turns out this process scales. It just gets better and better as you increase the atom number. That's why. Yeah. So I will give one more just quick note that when you think about using entanglement versus not using entanglement, I'm saying LIGO is. LIGO has been using non-classical states of light to enhance their ability to detect gravitational waves. It's a fantastic story. And I want to point out that they really didn't have to use non-classical light to improve their sensitivity. All they needed was to go to the US Congress and say, please give us another $3 billion, and we'll build another one next to the first one in Washington, and we'll build another one next to the one in Louisiana, and we will get the same enhancement in sensitivity. So think about entanglement as a resource. You should basically say, first you have to tell me what the classical constraints are. LIGO had the classical constraint of building another identical detector would take a lot of time and a lot of money. And that's where you have to make the judgment for yourself. Is entanglement, am I constrained by classical constraints that make it worth my time to use entanglement?
Thank you, James. Okay, so now let's thank James again. And actually now we will have plenty of time to do a conversation with James. So we have coffee outside, and then we have in the library this space where we can have a more relaxed conversation. So I invite you to take some coffee, and then we go to the library.